Well, that's pretty much it. So we looked at four different distributions. So one is a uniform distribution, and then we moved on to univariate Gaussian distribution and multivariate Gaussian distribution. And we also touched the basis of gamma distribution, and also we looked at exponential distribution. And here is one last note that I would like to add. So although we have seen different types of distribution, where indeed we were talking about a single distribution family. So what we have seen so far, where they were not randomly selected, they were actually rooted on a same representation of distribution. So that is called as an exponential family. So any members in exponential family, they can be written in the exponential normal form. So this is the definition of exponential family. So any member in this family, the distribution can be notated in terms of 1/3 multiplied by h and exponent to eta and t. And each of these terms has some special meaning. So eta, that is something called as a natural parameter or canonical parameter. T, a function of sufficient statistics. And h is a function of x, just a function, so it does not even have a name. And g eta, this is a normalization constant, that is a partition function. So what we are going to do on top of it, here is an example. So we studied Bernoulli distribution. So Bernoulli distribution can be notated in terms of zeta to the x, 1 minus zeta to the 1 minus x. You can write this down using exponent and log. So we give logarithm and take that back using exponent. So if you do so, we put exponent on the outside, and inside we can represent the same equation, x log zeta, 1 minus x log 1 minus zeta. And it can be readdressed as like this. And eventually we can sort of sort out things, one exponent term and another exponent term. Given that, what we want to do is try to match things using the template for the exponential family. Then we can find each of these items, and they have some special meaning. So that's the idea. So let's take a look at the case for Bernoulli distribution. So we understood the math work here and try to get the sense of it. So things in front of x, that is eta. So that is a natural parameter of the Bernoulli distribution. And that can be written as a log zeta over 1 minus zeta. On the other hand, well, in this case, we are assuming sufficient statistics, which is simply x. And on the other hand, in front of the exponent, we have exponent log 1 minus zeta, that is equivalent to simply 1 minus zeta. And this position was for 1/c eta. So we can say g eta is 1/1 minus zeta. And hx, there is no special vector left. So hx is simply 1. So this is one example how you find Bernoulli distribution belongs to exponent family. So we can find out some special meaning behind of natural parameter and sufficient statistic. Let's talk about in a minute. Now let's try to do the same on Gaussian distribution. The Gaussian distribution is given as some quantity sigma 1/sigma root 2 pi exponent minus square of the difference between my observation and mean and over 2 sigma square. Well, by the way, this is called as ERF function. Well, anyhow, if you sort out the upper part, you will eventually have these quantities. where this is paid, this Gaussian distribution in terms of exponential family. So there is some thought process. So you need to analyze what you have at hand and try to match with the exponential family form. So what you want to do is find out the coefficient in front of x in the exponent term. So you're going to have eta. In this case, you have vector. And sufficient statistics also given as vector. So x and x squared. And this part is 1 over c. So if you take 1 over exponent and this quantity, that is taking the -1 inside of exponent. So g eta is equivalent to exponent and some quantity. And eventually you are going to have hx, that is 1 over 2 pi. Well, checking some distribution is belonging to exponential family or not. Well, this requires a certain amount of practice. So, well, it's not really straightforward, as you see. So you need to study different cases. So I will prepare some homework problem. But well, anyhow, you need to practice them and exercise them on your own. So try to get the sense of it. But in the meantime, exponential family is generalizing one of the property that all the members of the exponential family, all the distribution models in the exponential family is following. So this allows us to take the likelihood function of the distribution. So like what we discussed there, where exponential family, it has a natural parameter, eta as a parameter, and we want to look at the distribution of x, the variable, random variable. That means we can expand and rewrite things in terms of the notation that we defined. So this is the definition of exponential family, or form of the template form of exponential family. Then we can sort out things this way. And at the end of the day, we are going to have a summation of the sufficient statistics. And if you take the log likelihood after it, so this was a likelihood. And if you put log in front of it, you can get the log likelihood estimator. So log likelihood can be sorted out in this way. And if you take the derivative out of it, you are going to eventually get this simple form. And at the end of the day, given this simple form, we can say some estimator, well, partial derivative of some estimator, but this is defining your parameter. That is again defined by the mean value of your sufficient statistics. So the eventual catch is very simple. So for MLE, the parameter should be adjusted based on the mean value of the sufficient statistics. So what we were doing here, for Bernoulli distribution, we try to find out what is sufficient statistics. So that is simply the observation x. And you want to get the mean value of the observation. Well, remember how we estimated the theta value for Bernoulli. That was simply the number of heads over number of trial. That is mean of the observation. And that is again clearly visible after analyzing things in terms of exponential family. So the sufficient statistic for Bernoulli is simply x. And in order to estimate the maximum likelihood, we need the mean of x. So that is what maximum likelihood was stating. So, and speaking of Gaussian distribution, again, this is the sufficient statistics. And in order to get the maximum likelihood of Gaussian, we needed to have mu, that is mean from the sample, and sigma square, that is variance from the sample. And x square is basically representing variance. So the definition of x variance was x minus mu square and taking the mean. Where if you want to be unbiased, then it's going to be 1 over n minus 1. But still, you need a mean value for x square in essence. So that is what this exponential family is disclosing. And from the analysis, so by analyzing things in terms of exponential family and sort out things to get the estimator for the natural parameter eta, we ended up having where always we need a mean value for the sufficient statistic or expectation for the sufficient statistic, and that is where this entire work process is disclosing. So well, that was pretty much it for the parametric density estimators. Let's stop it here, and if you have any question, let me know.